Good morning to all the participants. I welcome Dr. Sivamohan Reddy Garu, who is an associate professor in Department of Chemical Engineering, IIT Roorkee, and Sir belongs to Kadapa, and he is working in IIT Roorkee. So I request Sivamohan Reddy Garu to introduce yourself and start the session, sir.
Okay. So, very good morning to all my fellow colleagues. It is my great pleasure to be a part of this FDP program where I can share my research work to the people who are interested in the area of novel materials for different energy and environmental applications. So before going more in detail about the topic, so let me just give you a brief overview of my profile so that it will be easy for you to correlate with you people. So I have done my masters from IIT Kharagpur, and I did my bachelor's from Gayatri Vidya Parishad College of Engineering, Visakhapatnam. Then I moved to IIT Kharagpur to complete my masters. Then I moved to IISc Bangalore to complete my PhD in the year 2012. And from there onwards, I moved to York University, where I have worked as a postdoctoral fellow with uh, Janusz Kozinski, who is a collaborator for NASA Glenn Research Center, where we are developing the hydrothermal flame reactor for space applications. So after working over there for a couple of years, then I moved to, I have been offered as an assistant professor position in the Department of Chemical Engineering, IIT Roorkee. Then I joined here in the Roorkee in 2015. And from that onwards, I have been working as assistant professor from 2015 to 2021. So recently I've been promoted to the associate professor in the Department of Chemical Engineering. So my basic area of research is conversion of biomass into gaseous and liquid fuels, synthesis of nanoparticles using the biomass, and their applications for energy and environment. So this is the brief overview of mine. So let's go to the topic for the today's topic, that is carbon nanometal composites for hydrogen rich fuel gas generation. And before going more in detail about the things, I would just like to give you the glimpse of our Roorkee so that you can feel the actual scenario of how Roorkee and IIT Roorkee is looking like. So this is the overview of the IIT Roorkee, which is the top view from the sky. It's completely greenery. So this is our main building, which has been built more than 100 years ago. So this is the J.J. Thomson buildings, our administrative building, so which has been built in the 1847 year. So this is our library, our playgrounds. So this is the outside scenario of Roorkee. We have a beautiful mountains, very good cycling ride it is going to happen. So this is the Ganga Canal which flows through the city. In the middle of the city, you can see this Ganga Canal. These are the plains. This is the road view just beside the canal we have, and this is a wonderful beach that we have to, in the city. This is our auditorium. The morning view. Our playground. So this is one of the greatest building that, I mean, the bridge that we have, where you see that you have water flowing above the road actually. So these are the glimpses of our Roorkee. So now I think we can go to the actual course part that we were dealing with. Okay, so in the nowadays we have the biggest challenge is our solid waste disposal. So how we can dispose the solid waste that is going to be generated by the humans, right? From the human activities. Now, if you look out at the the waste. So you can categorize the waste, or you can depending upon the uh, uh, kind of your source you are having, we are generating a variety of waste. So that might be agri residues. If you have having the waste that is generated from the agriculture, that we call it as agri residue. If you have forest, we call it forest residue. If you have a municipalities, the whatever the solid waste that is going to be generated, that is going to have municipal solid waste, right? And if you have any industrial waste, so that is called as an industrial waste. Okay, so all waste are not going to be the same. So that's where the biggest challenge is going to pose for the researchers, how to handle variety of waste in a single unit. Now, if you look out at the good old days, or like the matured technologies that is already available to us, okay, or that is prominently implemented either in both developed countries or in the developing countries, we see that it is openly burned, right? So now what happens when you are openly burning any of your waste? So see, there is nothing wrong to burn the carbon material into the way in an open air environment. So when you burn the air, so if it is not completely burning, I mean that is if you have a partial combustion, okay, so that's where your problems is going to happen. So as long as you are doing it's a complete combustion, so you don't have any issue with the environment. Of course, you have an issue with the environment because of carbon dioxide emissions. However, nature is a beautiful doctor which can cure itself with the kind of damages that we do with the nature to the nature. So it can cure on itself, but it takes long time. Okay, now with the urbanization and with the urbanization that is happening across the globe very rapidly, so the kind of damage that we are doing to the environment is going to become exponentially. So as a result, if you see that the recovery of the nature to come back to its original position, it is taking its thousands and thousands of years. See, if you look out at any of your burning, or like in the source for your energy, right? So if you look out at the wood, so in the old days the wood is going to be openly burned, and they used to do all kind of the necessary or mandatory activities that is essential to for the existence of human beings, right? So now at that point of time, there was no carbon dioxide emissions, or like at that point of time, there was no carbon dioxide emission concerns at all. Why? What is the reason? Because at that point of time, the consumption rate of your woody biomass or the carbon materials was very less, and it was able to the rate at which the carbon dioxide is going to be emitted is going to be almost all equal to the rate at which the carbon dioxide is absorbed by the nature. So when you talk about absorbed by nature, I'm talking about the plants, right? So that's where you have some kind of carbon balance when we are dealing with the carbon sources in the olden days. Now, because of the urbanization and with the development, huge and variety of waste or variety of materials are coming into the environment, so which is very difficult for us to handle the things. One good such example is like the plastic, right? So though the plastic has been a wonderful material, but it takes hundreds of years, okay, to degrade the plastic by the nature, right? Which is not good sign for the nature or for the environment. So now as soon as you are burning the air in an open air environment, so you are limited by its oxygen. As a result, you see at the left hand side of my slide, you can clearly see that you have a black smoke that is coming out. So these are nothing but your particulate matters that is generated during the burning of your carbon source, right? So now how to overcome these kind of issues? So when you have lot kind of particulate matter that comes into the thing, so it is going to result in your air pollution, It also results in your generation of a variety of NOx and SOx components, which in turn is going to impact through the rains. Okay, so we need to make sure, as a research community, we need to make sure that these sources or the waste that is going to be generated from the various activities of humans, that might be during the household, or that might be during to the agriculture or by the industries. So one should be aware how to dispose these waste in an effective manner. Okay, and if you are looking out for any kind of, or if we are able to get any valuable value added product from the waste, okay, so then we should be in a position to extract that value from the waste, so that you can use it, or you can reuse it or recycle it for number of times. Okay, so now one popular since as we have been already know that the waste which is having a high rich in carbon content, so that can become as a potential force for the conversion of energy, right? So one such things that we usually come across is your any carbon source, I mean any source which is rich in carbon. Okay, so that if you can dry it, then you can burn it, and then you can extract the energy in the form of heat, or you can gasify it, you can generate the gaseous fuels, you can convert it into liquid fuels. Not only that, you can do the carbonization part, and then you can see the solid fuels. So now, depending upon the kind of process that we want to choose, or depending upon the fuel that is required by the community, we can choose a particular kind of conversion process, and then we can process the carbon waste that is generated from the different activities into useful material. So one such operations that we will be discussing today more in detail. Okay, so this is the typical energy consumption pattern of various fuels for the by the living systems. If you see that major contribution of the energy is going to be, all the fuel is going to be coming from your renewable sources, renewable fossil forces like coal and oil. So you see that we have oil, we have almost 34%. Coal is contributing nearly 27%. And another thing is the natural gas that we see is around 24%. So if you look out at the major part, the fuels that is contributed for the consumption across the globe, we see that almost all 85% is coming out only from the fossil fuel sources itself, right? And we see only very low portion, that is only 15% is coming from the nuclear and the other renewables sources. Out of these renewables also, you see that major thing or major fuel consumption or major energy that is going to be supplied is from the hydro, followed by your wind. And then the third one that we are looking at is your the biomass. So biomass is one such good source. Why we say that we are more focused towards the biomass? So if you look out at these other two form of renewable energies, or other renewable forms of energy like hydro energy, wind energy, solar energy, geothermal, these are all seasonal limited, right? So if you have a particular season itself, you have very high kinds of winds where you can generate huge quantities of electricity. The same with solar energy also. So you cannot expect the sun all through 365 days in any location, right? So that's where it is very difficult for us to harness the renewable energies. But as long as there is an existence of any life, you see that there is a biomass that is going to be generated. Even if after the death of the living beings also, whatever the biomass that we are going to generate, so that is called as a is also called as a biomass, but that belongs to a different category, that we call it as animal biomass, right? So as long as the existence of the life is going to happen, so the biomass is going to be generated, irrespective of wherever you are there, whether you are there in the ocean, or whether you are there in the during your on the land, or you even during in the space also. If a space human, I mean, if a human travels to the space, he is going to generate on an average of 9 kg of biomass per day per person. Okay, so which is very huge. If you look out, if you have a space mission of and the space missions is not going to happen only for one day, right? So we are going to have it for more than months, actually more than in terms of usually months. So large quantities of biomass is going to be generated from the activities of the humans and the other biotic life, I would say. Okay, so that's the reason why we see, irrespective of whether it is whatever the situation, so the biomass is going to be generated across the globe and across any time. Okay, irrespective of whatever the seasons, it doesn't have any seasonal constraints that that other renewable forms of energy is going to happen. And moreover, if you look out at the biomass, so biomass is usually rich in carbon content. Okay, so now as I've already discussed with you previously, where I have already informed you that in the olden days, that the combustion of your any carbon source results in the CO2 emissions, and then that is going to be not a problem. That was not a problem in the before a century ago, right? So because where there was no industrialization and no development, right? So at that point of time, the emissions that is going to be emitted is going to be absorbed by the plants or the trees, so which reduces or which neutralizes the CO2 emissions into the atmosphere. Now with the rapid growth, okay, so with the rapid growth of your development, that the energy that is the energy demand by the biotic life has become huge. So as a result, so there is a huge dependence or huge stress towards the consumption of your fossil fuels. As a result, you might have been already hearing a few news here and there that, like, fossil fuel reserves are going to complete maybe in another 50 years, 60 years, something like that, right? So if you look out at the biomass, so which is going to be generated quite often and very cheaply available, and this, if you look out at the life cycle of your biomass, okay, so though the fossil fuels also comes from the kind of biomass itself, but still you see that the biomass that we are going to use is usually defined as a carbon neutral source, because whatever the emissions that it is going to be emitted when you are converting it into any of the fuels, so that is going to be once again absorbed into the solar energy. Now if you look out at the fossil fuels, the time frame or the rate at which it takes its formation for the any of your fossil fuel source, it takes nearly millions of years, because how this fossil fuel reserves is going to be formed, you have any of debris or any of the carbon sources that is going to be buried deep in the deep inside layers of the earth during the natural calamities, and there it undergoes many physical, chemical and thermal variations, and through which the carbon source is going to be converted into some kind of fuel kind of material. So that might be either natural gas, that might be either oil, that might be the coal, right? So these biomass that is going to be generated is going to be converted into the fossil fuel source, and these fossil fuels reserves are going to be explored and extracted, through which we are able to convert them into fuels like both gases and liquid fuels. Now if you look out at these scenarios, so the rate at which we are consuming the fossil fuels and the rate at which it is going to be formed, it is not going to be balanced at all, right? So that's where we see that the fossil fuel route is not going to be beneficial in terms of either carbon conversion, in terms of either carbon emissions, and also the rate at, and also the reservation of your fossil fuels. But now if I'm going to convert this biomass into through this route, okay, so through the biorefinery route, I just take without any having the natural processes, if I'm going to use any of the thermal and chemical processes, okay, where I can directly convert the biomass that is available to the biotic life into some kind of value added materials like fuels, for example hydrogen, methane, okay, and bio oil, right, and biochar, okay, charcoal. So if I'm going to convert these biomass through the chemical, physical and chemical thermochemical processes, so then we see that the rate at which it is going to be emitted, the carbon emissions will be somehow balanced, okay, at which the carbon dioxide is going to be uptaken by the plants. Okay, so that's where we see that the biomass, the biorefinery route that we are proposing is going to be a carbon neutral source or carbon negative. Sometimes it might be the carbon negative source, or carbon negative source where you see that carbon dioxide emissions is going to be further less. So if you look out in the atmosphere, so now it is somewhere approximately around 400 ppm of CO2 is going to be is present in the air, so which is significantly rising by 1 or 2 ppm every 2 to 3 years, right? So we need to make sure that how to reduce this CO2 emissions in your atmosphere so that you can reduce this problem of global warming also, right? So one should be aware or one should be driving out, looking out for those kind of technologies where you can reduce the carbon emissions and where we can uh, be less dependent on the fossil fuel source and develop the fuels from your renewable sources of energy like wind, solar and the biomass. Okay, so once we know, now we know that biomass is going to be a it's a carbon neutral source. Now the question is, so what kind of biomasses can be there, right? So as I've already mentioned, so whatever the activities that we that the biotic life is going to happen, that will result in some kind of residues. So those residues can be considered as a biomass resources. So that might be ranging from your sewage that we are going to generate in every household, or might be the agricultural and crop residue that it is going to happen, or the forest residues that we have, that is large quantities of wood, or the variety of leaves that is going to be there. So all those comes under your biomass resources. Even the municipal solid waste that we generate every day, right? So that also can be considered as a biomass, and there is a huge research that is going on to convert this MSW into a value added product that might be either into conversion of your fuels or might be some other chemicals. And not only that, it is going to be the animal residues, okay? So even the meat industries that you are talking about, and the residue that is going to be generated like fecal ones, so those are also comes under the category of your biomass, but that is falling under the category of animal residues. And all the industrial residues which are rich in the carbon part, okay, so that also we can consider them as a biomass resource. So now from these is, if you look out at these kind of sources, we can feel that, like, so the biomass is located everywhere around you, right? So now it's only the as a research community, we need to make sure that how these biomass or the carbon rich sources is going to be converted into useful materials, right? So as I've already said, that biomass is going to be having a huge potential for the energy source because of its high rich in carbon content and its cheap availability. And moreover, you can generate it at any point of time at any globe, and large quantities is going to be generated across the globe, right? And typically the composition of a biomass is going to be classified into three is going to be made or measured in terms of three contents. One is your cellulose content, hemicellulose content and lignin content. So cellulose typically comprises of 30 to 45%, hemicellulose comprises of 20 to 30%, lignin comprises of 10 to 25%. Okay, as I've already mentioned, the biomass can be a bio-neutral, carbon neutral one, because the carbon dioxide that is going to be emitted through the biorefinery is absorbed by the trees and plants across the globe, where it can reduce or it can uptake the CO2 emissions that is made by the from the biomass. Okay, so now let's try to see, or I'll just give you an overview, like, what kind of conversion processes are available. Okay, And the most popularly used conversion technique where we see this biomass into liquid fuels is that is nothing but your bio oil or pyro oil or pyrolysis oil that you might be well known. And we see that, so you have it biomass, so you first need to buy this dry this biomass that you are going to have it, to make sure that its moisture content is going to be less than 10 weight%. So that's where your major energy is going to go, or like the energy input for the entire process, usually 90%, 80 to 90% of your energy that is required for you to convert into the pyrolysis plant for the conversion of biomass into fuels, that is liquid fuels, is going to happen or result because of your drying process. Now, once you dry your material, then you have to grind it to less than 5 mm, fed to a reactor which is comprising of very high 500 degrees centigrade, typically where you have a high heating rates. So this pyrolysis can be divided into three further processes. One is your flash pyrolysis, fast pyrolysis, and slow pyrolysis. In the flash pyrolysis, you have a very high heating rates where you are going more than 500 degrees centigrade per minute. Okay, or more than 100 degrees centigrade per minute, right? So when you are going to flash your carbon source with a high heating rates at high temperatures, so your carbon is going to be converted into the liquid fuel. That's where you see that you have high quantity of bio oil yields when you have during your flash processes, right? So another kind of process that I have already said, it is a fast pyrolysis. You can have a very high heating rates, more than 50 degrees centigrade per minute. So there also you have a very high yields of bio oil. But when you have a slow pyrolysis, you have less quantity of bio oil and gas, and your main focus will be with the solid biochar that you are going to get it, right? So that's how the pyrolysis process has been classified as, depending upon the temperature and the heating rates that has been mentioned. Now once the biomass is fed to your pyrolysis reactor, we see that it gets degraded into three compounds, three phases, that is solid, liquid, and gas phase. Now the gas phase usually comprises of hydrogen, CO, methane, and carbon dioxide, but of different concentrations. Now these at the top of, from the top of the reactor, it goes to a cyclone separator. So where you can separate the gas from your solid particles, that is the solid particulate matter that we are going to see. This hot gas is going to be quenched, and the product gas is going to, the product mixture is going to be quenched. So as soon as it is, you are going to quench it, you are going to have a liquid phase, that is nothing but your bio oil phase, and then you have the liquid and solid. We are going to the liquid and the gas, we are going to separate it over here, where you are going to get the pyro gas, which is going to be directly burned to extract the energy from that is essential for you to maintain your reactor conditions. Okay, so this is how a typically the pyrolysis process diagrams looks like to convert the biomass into liquid fuels, right? So this is a thermochemical route that you are going to have. So other kind of conversion route that we popularly known is now the gasification technology. So this gasification technology is a well-known technology which has been known to the research community over the decades. And we see that any carbon source, that might be a coal, biomass, petroleum coke, or residue, or any waste, so that can be fed to a gasifier. And you see that as soon as you fed to the gasifier, which is maintained at very high temperatures, typically in the order of more than 1000 degrees centigrade. Some gasifiers might go as high as 1800 and 2000 degrees centigrade also. Okay, and as soon as you do it, so most of the carbon material that is there, that is going to be completely gasified, and you have very less quantity of the solids. Those are going to be collected at the bottom, and whatever the products that comes out from the gasifier is fed to a cyclone separator, where you can remove the gas and the solid particulate matters. And if you have any sulfur acid gases present over here, so you are going to remove those acid gases, and then you are going to clean it up, or you are going to send it to the remaining gases like carbon monoxide and hydrogen. Some is being fed to the syngas, where you can synthesize the fuels and chemicals, and partly of the hydrogen that is going to be generated can be directly implemented as a transportation fuel, or to generate the energy via the fuel cell, all from the direct combustion of the things, right? So apart from that, so you need to, when you want to gasify the things, unlike in pyrolysis is going to happen in an inert environment, whereas gasification is going to happen in the partially oxidizing environment, right? So when you see that in the partial, so we might require the air or the oxygen that is required. So what happens when you are going to we need to make sure that the air, the oxygen that is present in the atmosphere is going to be separated, and then can be fed to the system via atmospheric separation, air separation unit. So air is usually fed to the from the hydrogen, whatever you are going to get. So you are going to take it to a combustion or a turbine engine, so where you can generate the electric power over here. And the air that is coming out can be fed to an air separation unit, and from here you can see that the oxygen is going to be separated, and a part of energy that is required for you to water, that is the steam, in the form of steam. Okay, so that is going to be generated over here in the steam generator, and partly it is fed to the system, and partly you are generating once again the energy. So this is typically how a gasification process look like in the industries, where you are going to, that might be either the feed source might be either coal, or might be the biomass, or a combination of those two things. So this is how typically your energy flow, or the generation of your gaseous fuel is going to happen for any of your carbon sources, right? So I have already discussed about the pyrolysis and the gasification process. So these both comes under the thermochemical routes. Okay, now if you look out at the biological routes, so if you look out any biological routes, so we see that biomass is usually whatever the biomass that it is going to be, we usually harvest it, store it, and then we go for a pre-treatment process. Now if you look out at the conversion of cellulose to your ethanol, right, all the liquid fuels that we are going to talk about, okay, so that comes from the source of your cellulose, or from the sugar, right? So sugar, cellulose is going to be hydrolyzed, where you are going to once you hydrolyze your cellulose, you are going to get the glucose and glucose forms, and then glucose is going to be further fermented to form ethanol, and once you have this ethanol, you are going to recover that from the fermentation plant. So this is how typically the biological conversion of your biomass is going to happen towards the generation of your liquid bio oil, right? So these are the different conversion routes that is existing for the conversion of biomass into fuels, right? So we have discussed about thermochemical routes, and we have also discussed about the biological route. Now if you look out at these conversion routes, so each conversion route has its own limitations. Now let's try to see what is those limitations. If you look out at the thermochemical processes, so we see that, as I've already said in the first process, that where we are going to have this pyrolysis process, we need to reduce the moisture content to less than 10%, right? To make sure that it is going to be properly grinded and then fed to the pyrolysis reactor, right? Now if you look out at the biomass which is rich in moisture, like agri residues, human whole residues, all the animal residues, the fecal residues that you are talking about, these are all rich in your moisture content. So you need to provide the additional energy to remove the moisture from the carbon sources, right? So that means you need to provide the additional energy that is required for you to reduce the moisture content. Now the second, or the key problem that we usually encounter whenever you are burning, or whenever you are going to have an thermal treatment, you see there is a lot of formation of tarry compounds. So this tar is nothing but your non-condensable carbon paste kind of thing, which is thick slurry kind of thing. So these, when mixed with char, it forms a clinkers, and it is become very difficult for us to handle in the gasification process. And the third one that we see is because of the above limitations, we see that the gas yield is going to be significantly reduced, right? So these thermochemical processes, or you need to have a very highly sophisticated designs, or you need to have very high temperature, high pressure reactions where you can enhance the gas yield significantly, right? So coming to the biological ones, so we require, so it typically takes usually hours, right? Not even minutes. It will take typically hours of fermentation process, so that you will able to get a very low quantity of yields, and you have a very different biological and stability that is going to be specifically maintained, so that you would be able to get the required bio yield at the optimum conditions, right? So if you look out at the biological conditions, so pH should be typically maintained in the range of 4.5 to 5.5. So during your alcoholysis part, whereas in your acetogenesis part, so you will see that pH is going to be somewhere around 3 to 4, right? So it's all depends upon what kind of metals that you are, I mean, what kind of components that we need to generate. Okay, so you need to have very peculiar conditions for biological conversion routes, and moreover it requires very high residence times that limits these kind of operations or conversion techniques. Okay, now how to overcome these challenges? So researchers have found a way where we can overcome the handling of variety of waste with variety of moisture content. So that how we can do it, by using this supercritical water gasification part. So now wet biomass can be treated even without a drying step. So why it is dry, why there is no requirement of any additional energy over here? Because you are using moisture itself or the water itself as a medium. Okay, so you see that then you don't need to have any drying step that is required for us to go for either gasification or pyrolysis process, right? So whatever the energy that is required for the drying process can be ruled out over here. And moreover, whenever you are, see, it is once you generate the gas, like, hydrogen gas. So hydrogen is highly flammable along with methane, right? So you have hydrogen and methane that is going to be there, because once you separate carbon dioxide, so then you will be left over with hydrogen, methane, and carbon monoxide, right? So these gases are highly flammable, and usually the storage pressure, if you look out at the natural gas storage pressure and hydrogen gas storage pressure, these storage pressures are somewhere around 200 atmospheres. Right, so whatever the gas that you are going to generate, you need to compress them towards nearly to 200 atmospheres, and then you have to store it for their process operations. I mean, you have to store it for them at those pressures if you want to use it at a later part, right? So you require an additional compression energy that requires for your storage of your highly flammable gases like hydrogen. And the key part over here in the supercritical water gasification is you have very less quantities of char that is going to be formed, and the tar reduction, that is the non-condensable forms that it is going to be formed during the thermal or during the hydrothermal treatment that you are going to happen. So that is going to be negligible. As a result, we see the most of the carbon that is present, it is going to be converted into the gases to a greater extent. And furthermore, your reaction rates are very high. Okay, the reason why you have, so since you are using it at very, since you are going to use it at though it is at a normal temperatures, but your reaction rates are high, because your fluid or the medium that you are going to talk, it is going to take or dissolve all kind of organics that are generated during the degradation process. Now when you say that all kind of intermediates, means whenever you are going to have a degradation of any of your biomol or the carbon molecule, so it generates another carbon molecule, right? Now what happens in kind of normal processes, you see this carbon material is not, this carbon molecule or the intermediate that is generated, that be, if that is insoluble in your water medium or in the medium that you are going to have, then you have a mass transfer limitation, and you have the resistance that is going to be offered from the particular phase, and as a result you see that the reaction rates is going to be very much less. Now as soon as you are taking it to the supercritical conditions, you were all the carbonaceous materials so which are usually insoluble at normal room temperature at STP conditions, though it becomes completely soluble in your supercritical water, and your reaction rates are pretty fast. That's the reason why we see that the degradation rates of your supercritical, I mean, carbon materials in the supercritical water will be in the order of minutes rather than in the typical any of your thermochemical processes that you talk about. So those typically will be there in the order of your in the order of hours, or in the order of hours or in the minutes. But if you look out at the residence times for a continuous process in case of supercritical waters will be in the order of seconds or minutes, right? And moreover, so when you look out at the overall process, so we need to make sure that whether it is a cost effective process or not. So one of the study has been suggested that supercritical water technology is going to be the most economical hydrothermal route through which you can say that bio waste is going to be converted into the gaseous fuels, typically hydrogen rich fuel, in comparison with the conventional processes like biomass pyrolysis method, electrolysis methods, wind method, or the PV electrolysis, like the solar electrolysis method that we are talking about. So these conveys that, like, the supercritical conversion technology is going to be a useful or process, or might be a competent process with the conventional technologies that exist for the conversion of biomass into fuels. Okay, so since you are already aware, so now let me just show you what is a supercritical water first. Okay, so the idea of this
Starting fire.
so if you look out at the how this supercritical water has come into the existence. So when one of the there was a building in the fire, there was a fire in the building, and it was an enclosed building actually. So now when the firemen used to process the water, use the water to get down the temperatures of your fire inside that enclosed space, instead of decreasing the temperatures, it has been rapidly increasing. So then they found what might have been the reason. So whatever the carbon material that is present inside that enclosed space, when you are throwing water into that, so it forms a kind of different fluid phase where the carbonaceous materials coming into the contact with the water, it gets combined and it forms, instantaneously reacts and then produces the oxidation process, which will effectively convert these carbonaceous matters into the carbon dioxide and other water material, right? So you have a variety of waste mates that is going to be, as I've already told you, that biomass can be generated across the globe from various activities that might be ranging of anything. Now, if you see that, as soon as this is how a typical phase diagram of any component looks like, right? So if you are going to increase the temperature and pressure, so you see these water droplets is going to be converted into a single white phase. Okay, so where you see that water, when it combines with any of the carbonaceous materials, gets converted into carbon dioxide. So variety of applications can be found for this supercritical water oxidation, where we can see that where we can see this kind of applications not only in the space marine applications and also but the fuel generation. Okay, now the main problem with this supercritical water is, as you see that water is going to have a very good solvent for your salts, right, at the STP conditions. Now as soon as you take it to the supercritical conditions, the salts that are usually dissolved or present in your water, so those gets precipitated and then it eats away the reactor or corrodes the reactor material. So one should be aware that that what kind of how the TDS is going to be there in the water before you start the supercritical water reaction. So this is how the your reactor material gets corroded if you are going to use it for a longer specific of time. Okay, so NASA has developed some peculiar kind of reactor where they have studied how this salt precipitation can be overcome with the supercritical water, and they have devised a reactor on which I have also typically worked for a couple of years, where we have generated flames inside that particular reactor to understand the phenomena of the generation of the flame inside that particular reactor. Okay. So maybe I think I can share about those details maybe in any of different lecture. So that is a different area where we have generated the flames. Okay. So now come, let me explain you how this supercritical phase is going to be formed. If you look out at the figure over here, that's a phase diagram of water. You see that if you are going to increase the temperature and pressure along the vaporization curve, okay, at a particular point, the distinction between the vapor phase and the liquid phase is going to get disappear. So that point we usually call it as a critical point. This you can find for every component that we exist, so that have a critical point. Okay, so now for water it is going to be at around a temperature of 374 degrees centigrade and at a pressure of 218 atmospheres, that is nearly 22.1 megapascal. So now if the operated conditions are beyond this temperature and pressure, so then whatever the fluid or the water that is going to get existed, so that is called as a supercritical fluid. Okay, so now the question that we usually encounter for any of these conversion processes is, see, since you are saying that, sir, the temperature is going to be very fine, it is okay, 374 degrees centigrade, but the pressure you are saying that it is going to be very much high. So how can you justify in terms of energy consumption? So now if you look out at the enthalpy versus temperature that we are going to have plotted over here, so now the energy that is required for you to take that a stream of water from 25 degrees centigrade to 700 degrees centigrade at 1 atmosphere and at 300 atmosphere, so it is almost all equal. So this conveys, or this diagram conveys us that this hydrothermal process can be a competent process with the other thermochemical conversion processes that exist over here, like pyrolysis and gasification. So now one more additional advantage of this supercritical water, as I've already said, the gases that is generated, that is both the organic and inorganic gases that you are talking about, so those are completely soluble in your supercritical water, which enables the removal of your mass transfer resistance or the phase transfer resistance, right? So whenever you have this solid phase, liquid phase, and this is so, but now here in supercritical gasification you have a single homogeneous phase where your components interact with each other, gets converted into your useful materials. Okay, and the second thing that I have already mentioned is that this biomass can be processed without drying. That means you don't require any additional energy for your drying process. Okay, now what are this how are the thermophysical properties is going to be changed with the change in your temperature and pressure? Now if you look out at the water, so the typical critical point of your water is 374 degrees centigrade and 22.1 megapascal, whereas for carbon dioxide it is 31.1 and 7.4 megapascal. For ethanol it is 241 degrees centigrade and 6.1 megapascal, whereas for benzyl alcohol it is 403 and 4.6. Now the reason why we have mentioned these things is the most popularly used supercritical fluids are water and carbon dioxide, because these are non-flammable one. The key thing is, see, whenever you are taking about, you need to make sure that the fluids is not going to be non-flammable, so that you can handle it very safely. Now if you look out at these things, you see at the supercritical conditions you can tune your thermophysical properties like compressibility, right? You have a very low viscosity, that means you are you don't require high energy for you to transport the fuels, and you have a very high diffusion coefficient, which means that the reactions is going to happen very quickly and there are no mass transfer resistance. You see, you have a dispersion, that means any of your carbon or the carbon source or the gases can be dispersed in your supercritical fluids very effectively, right? And you have very high permeability, which makes sure that it is going to be effectively used to extract some kind of components from your solid biomass that you are going to happen. So even because of these tunable thermophysical properties, so supercritical finds applications in variety of fields, like in for your drying applications, for your extraction process, okay, and for your drug loading process, for your degradation process, okay. So but that's all depends on what kind of conditions that you need to operate. For example, if you see that biomass, if I want to convert it into energy, I don't require to use the carbon dioxide over there. The reason why I don't require is its critical point is very much less, right? But if I'm going to use water as a medium, so then since the degradation of your biomass also requires high quantity of energy, and my critical point of water is also almost all similar to that of the degradation conditions of the biomass. So if I use water as a medium, so then I will be able to promote the reaction rates effectively, and thereby I will be able to get the large quantities of my gases or liquid fuels that we are tuning out for. Okay, so as one more beauty of your supercritical fluid is if you look out at the density, which is usually 1000 kg per meter cube, but STP conditions, it is going to be almost all as low as less than 100 kg per meter cube at high supercritical condition. Now what happens over here? So as I've already said, if you are going to move along the vaporization curve, so the density is going to be decreased. As a result, your diffusivity of your component is going to be very high. So the typical order, that means you can improve the diffusivity of your water effectively from 10 power 9 minus 9 meters square per second to almost all 10 power minus 4 meter square per second. So that means almost all 10,000 times you will be able to improve your diffusion coefficients. So that means you are able to promote the transport properties of the molecules effectively when you are using the things. And the another thing is your ionic product. The ionic product, that means it is effectively able to generate the ions like hydronium and hydroxyl ions at the supercritical, at the critical point of your conditions. That means these generation of these ions like hydronium and hydroxyl ions, so enables to act as an acid base catalysis. So that's the reason why you see the supercritical water or the near critical water or the conditions at which you are maintaining at the critical point, so it generates acid base. So these acid base can act as a catalyst and improves your hydrolysis reactions, so that you would be able to degrade the polymers, the biopolymers that are like cellulose, hemicellulose, and the lignin into its respective components, and these respective components will further degrade in the presence of ions or in terms of radicals, depending upon the operating conditions we are choosing it. Okay, so now if you look out at the thermochemistry, I'm just summarizing it. So you can see that the first part is homogeneous medium. It is able to dissolve a variety of gases and also the carbonaceous materials, which make sure that it is going to be homogeneous medium, thereby removing the mass transfer resistance that it is going to happen. The second thing is, as I have already mentioned, so since water is going to be used as a medium, so if you look out at any of your gasification process, reforming and the water gas shift reaction are very key reactions to promote the hydrogen gas yields, right? So if you look out at any, maybe in the coming slides, I can show you. You can see that carbon materials reacts with water, so there it acts as a reactant. As just a few minutes back itself, I have told you that it acts as a catalyst depending upon the generation of the free radicals and also the hydronium or hydroxyl ions. And not only that, it also acts as a solvent where you are going to improve the diffusivity and decreases the viscosity and surface tension to a greater extent. And as I already mentioned, these thermophysical properties like high diffusivity and low viscosity is going to happen for your is essential for us when you are dealing with these supercritical processes, to make sure that you involve or to promote the reactions very quickly. And depending upon the kind of operating conditions that you are going to happen, so it is going to degrade, or the biomass going to be degraded via ionic mechanisms, or if the operating conditions are beyond the supercritical point, that is typically more than 600 or 500 degrees centigrade, you have a free radical mechanisms. So as a result, these technology is going to found application in either in the gasification process or in the oxidation process. Okay, so now let me just explain you how this thermal gasification is going to happen. If you are going to feed a carbon source to a gasifier, typically in the range of greater than 200 degrees centigrade at near atmosphere, or like maybe 1 to 5 bar typically. Okay, that might be happen in case of your nitrogen, air, or water system. So that will result in two components majorly, that is your hydrogen, COs, methane, and carbon dioxide, and other hydrocarbons is going to be generated. Along with that, you have a char and tar that is going to be formed. So now, if the typical operating conditions of your supercritical gasification is typically around 400 to 700 degrees centigrade, and the pressure is around 23 to 30 megapascal, that is nothing but 23 230 atmosphere to 300 atmospheres typically. Okay. So fine. So now we know that, yeah, so we have finalized our degradation process. We know what is a biomass, right? But the complexity that comes is, say we have a biomass is very complex one, and we know that from depending upon the kind of activity that is involved, you are going to generate a variety of biomasses, right? So the each biomass is its unique in its own style, right? So it is quite difficult for you to understand how this the degradation of biomass is going to happen with the real biomass. Now, as a engineers or as a researchers, first we will identify the key components and how these key components are going to be degraded, and how these key intermediates are going to be degraded into your gaseous fuels first has to be known, right? So there are many simultaneous reactions that is going to happen, simultaneous series and parallel reactions that happens during the degradation of biomass, during the biomass at the operating conditions to convert it into hydrogen gas, right? So it is very difficult for us to analyze the thing. So we will start with the degradation with the model compounds. Okay, so these are typically the biomass components. As we see that you have any, if you take any of the plant or agri cells that you have, so it is going to have three layers. One is your crystalline cellulose, so the cellulose part that you are going to have any of the plant cell. Okay, so it have a cell wall, and if you look out at these things more in microfibril in detail, you see you have a crystalline cellulose at the top and hemicellulose, that is sugars, that is going to there. These cellulose and sugars are going to be binded with each other with the form of, or with the help of your lignin material. Okay, so that is your binding material, so which is very difficult for us to degrade. And these binding, the components of these binding materials, nothing but be coumaryl alcohol, conferryl alcohol, snapel alcohol, right? So these are the three components, and these are the few model components that you need to understand before to go more in detail. As we see that cellulose, so is nothing but the combination of the polymer of your glucose molecules, which is going to be bonded at the, have a similar structure like this. So where you see the components are going to be bonded with each other using beta 1,4 beta glycosidic bonds, and it forms a complex structures of like cellulose one. So this is the hemicellulose one, where you see that C5 sugars, it is C5 sugars like pentose sugars is going to be associated with each other, and it forms another polymer that is going to be. The third and keymost part is your lignin one, which is very hard to degrade and very difficult to degrade. That's the reason if you see it any of your fermentation processes, we usually typically remove the cellulose and hemicellulose initially, and the lignin is going to be separated, and whatever the cellulose and hemicellulose that is separated undergoes alcohol, undergoes hydrolysis to form the sugars, and these sugars are further fermented to form the. So the lignin material is the binding material, which is hard to degrade. Okay. Now, as I have already told you about this conversion process, just I will give you an overview of how this gasification of biomass is going to happen. If you supply the heat, it results in three major fractions. One is your gas fraction, liquid fraction, and the solid fraction. And if you are going to have this, the major problem that we are going to have is tar. So we apply some kind of catalyst so that, and the steam it is going to be generated, steam is going to be also introduced, where this tar is going to be reformed into your permanent gases like carbon monoxide and hydrogen. And these carbon monoxide and hydrogen further undergo water gas shift reaction to form your hydrogen and carbon dioxide. This is how typically the gasification of biomass is going to happen in the overview. Okay, so furthermore in detail, if you look out at of any of your metallic catalysts that you have, okay, so these usually dehydrogenase, or it removes the hydrogen at the things using the rearrangement section, or it might interact with the oxide things and then reduces or removes along with the formation of water. Okay, and it might, when your hydrogen is going to be removed from the carbohydrate, you form these kind of free radicals, okay, or generating the alcohols and acids, as I've already mentioned. So your key intermediate that it is going to be there is your alcohol and acid. So once we understand this degradation of this acid and alcohol in the supercritical water, then only you would be able to understand how the catalytic process or the carbon metal composites is going to work. Okay, so if you see these things, so these metals should have a potential to cleave these CC bonds, so that you get hydrogen and carbon monoxide, and you, it has also should be have a potential to cleave CO bonds. Instead of CO2 formation, we need to have a methane formation, and we need to make sure that this hydrogen and CO that it is going to form further interact with each other to form the water shift gas reaction. And these are the desirable catalytic properties that you need to have it. Okay, so this is the typical general mechanism of your biomass. So I'm not going to forward there. So let's start with the degradation of your the formic acid, that is the key intermediate that is formed during your degradation of process. So this is how typically your HCOOH, that is acid molecule, where you have hydrogen attached to one of the carbon. Okay, so if you are going to have a OH bond decision of like this, so you are going to have these kind of radicals that is going to be generated, right? So you have HCOO radical. Okay, so where you can see that the H radical, or the H radical that is going to be dissociated from your OH bond, interacts with OH radical to form water, and also the vice versa. If it is reacting with another H radical, it generates your hydrogen or water is going to be generated to generate this formaldehyde acid radical that you are going to have. So if I am further going to remove this H radical over here, so then you are going to get the linear molecule, that is carbon dioxide molecule. Now another session that might be possible is your CH bond session. So then you have HCOO session. Okay, so if that is going to have, then you have an alcohol radical. Okay, so these radical further interacts with the OH radical to form water, or if H, then it is going to form. Now the same thing, if I'm going to remove the H radical, then once again it results in the formation of CO2 radical. And if I'm going to have a CO bond session like this, then you have a formaldehyde over here. Okay, so HCHO radical. So once if you are going to remove this H radical over here, so then you are left over with carbon monoxide. This carbon monoxide, when acted with your OH radical, it results in the formation of carbon dioxide. So this is how the degradation pathway of your intermediate acid molecules is going to happen. Instead of H over here, you might have another functional groups, or another chain molecule, that is R, that might be methyl, that might be ethyl. Okay, any kind of acid molecules can be over here, but it follows the typical kind of reaction pathway. Now let's try to see how this alcohol is going to be degraded, which is an intermediate. That is, we'll go with the simplest molecule, that is methanol. Okay, so the same thing, OH bond session. So you are going to get this kind of CH3O radical, which gives rise to the formation of methane gas and hydrogen gas. If I'm going to remove H over here, so then I'm going to get formaldehyde, which further interacts with OH radicals to form your HCHO formic acid. And this after removal of hydrogen is going to get your carbon dioxide molecules. Now, if I'm going to remove the hydrogen over here, you are going to get carbon monoxide. So this carbon monoxide, when upon the interaction with OH radical, results in the formation of hydrogen and carbon dioxide. Okay, via water gas shift reaction. So if you have a CH bond session over here, so you see that you are left over with CH2OH1, and then it interacts with OH radicals to result in the formation of water things, and at the same time it is able to generate your hydrogen gas and the methane gas once it interacts with the methane radicals. Okay, so this CO bond is going to have a session over here. So then you have a methyl radical which which interacts with your H radical to result in the formation of H2O, or OH radical when it gets interacted with H radical result in the formation of methane, or if it result in the interaction with other methyl radical, results in the formation of ethane. Okay, so this is how typically the intermediates is getting degraded during the supercritical water. Okay, now let's come to this catalytic part. So you know that the catalyst doesn't involve in any of the reaction, but it reduces the activation energy that is required. So as a result, you see that the reactions are proceed effectively through a different path, right? Now, what happens for the catalyst if you are going to treat them thermally at high temperatures? What happens? So, if you have any catalyst like this, like a powdered catalyst or some kind of granule material, so when you are going, if you don't have any support, so what happens? So these things forms a big clunkers kind of thing, right? That gets agglomeration kind of thing, and then you form a big lumps kind of thing, which is not difficult for, which is very difficult for us, and thereby it loses its activity. Now the second thing is if you have a supported catalyst. Okay, so if you have a variety of supports and you have a catalyst supported onto your support, like that might be aluminum, carbon, or that might be any of materials that you are going to look out for. Okay, so these also will lose the activity once you are going to support it, these things. So the carbon get deposited over these active sites, and thereby reduces the activity of your catalyst that you are looking out for. Now the other key problem that it happens during this catalytic process is you lose its activity because of your chemisorption. That means some of the intermediates might come and sits on your active surface or on the active sides of your catalyst, and thereby reduces its activity. Okay, now the third and key most part is your coking process. Since biomass is a carbon source and you are using very high temperatures, so we see that the carbon that is going to be generated during the degradation process, it sits on the catalyst surface, or coke deposition is going to happen, which reduces the effective surface area and also the catalytic activity of your material. Okay, so these are the issues that are related to the catalyst. So now I have given you the overview of the degradation process, both the conventional one and the hydrothermal one, and what are the issues and challenges, that how we are overcoming it. Supercritical gasification I have already mentioned. Now if I am going to use the catalyst, let's see how it is going to be improved. Okay, so for that, so in our study, so we have chosen three kind of biomass. That is, one is your agro residue, that is banana pseudostem, and another is your sugarcane bagasse and mosambi peels, are the three variety of biomass that we have studied, or that we have chosen for our study to see how this catalytic supercritical gasification, or the formation of this carbon nanometal composites, is going to enhance our hydrogen yields. Now the reason why we have chosen banana pseudostem. So if you look out at the banana production, so India is one of the largest producer. So where we are almost all producing nearly 31 million metric tons of banana over the year, right? And you see that when you are going to have this banana pseudostem, so you see more than 85% of your plant, okay, is going to come under the residue part. Okay, now these residue can be potentially converted into either any of your value added chemicals. It might not be only specifically that we can look out for the thing. So you can see this, you can extract it for your fiber things, even that has been used for your fermentation for the generation of your alcohols also. Now we have chosen sugarcane because sugarcane also India is the second largest producer. Okay, and it also, this plant production also, crop production also results in almost all one third of its residue, which can be having a high potential to convert it into any of your visible materials. Now we have chosen the Mozambique because it is going to be rich in your lignin content, and we see that it is almost all India is your fourth largest producer of your Mozambique or the oranges, and we see that the residue that we are going to get from these fruits, it is from the crops, it is almost 50 to 60%, which can be effectively converted into kind of variety of fuels or might be any other enzymes or the value added products. Okay, so we have studied, so we have fixed our biomass depending upon its availability in India and their high cellulosic content, and we have chosen three metals or three catalysts which have been popularly used during the degradation of your carbon sources. So the primary one that we usually that is properly implemented, see, for any process you are going to, for any reaction usually we are going to use nickel. It is cheaply available and it's have high activity for your cleavage of your CC bonds, CO bonds, and this OH bonds. So that's the reason why we choose nickel. And ruthenium have high potential to cleave CO bonds and promote the formation of methane. So that's the reason why we have chosen ruthenium. And iron have a high activity for your ring opening things, like the tar components that we are talking about, right? So those are nothing but your phenolic components, which are ring shaped components. So these ring shaped components is going to be effectively cleaved in the presence of your iron. So that's the reason why we have chosen these three catalysts, where these catalysts can be, or these metals can effectively promote the hydrogen gas selectively via reforming and cracking reactions. Okay, so this is the process that we have implemented in our lab or developed in our lab to make sure that we are going to generate the nanoparticles inside your biomass matrix right at the front end itself, and then subject these nanoparticles embedded biomass to sub and supercritical gasification to yield a hydrogen rich gas mixture and the nanometal carbon hybrids. Okay, so now typically what happens, so we have chosen any kind of biomass, we have just taken it, grinded it into powder or might be paste. Okay, so then we have mixed it with the metal salt solution, that is might be, if you are using nickel, then it is going to be nickel nitrate. If it is ruthenium, it is ruthenium chloride. If it is iron, it is going to be iron chloride. Okay, and these, when you are mixing it in the metal impregnation process, the metal particles gets associated with or gets absorbed onto your carbon matrix. These nanoparticles embedded biomass matrix now have the metals inside it. These metals acts as a catalyst during the degradation of your process and thereby promotes the things, your hydrogen things. So now let me just tell you how this impregnation process is going to be done. So we have chosen the biomass. So that is going to be pulverized. We made sure that it is going to be reduce its size to less than 1 to 2 mm. And then we, through a magnetic stirrer, we have mixed this biomass and the metal salt solution. And then we have, for a specific period of time, so then we have filtered it. And then once we filtered the things, normally for experiment, we will directly take this wet biomass and then subject it to our supercritical gasification. But here I have chosen drying for our characterization part, because I cannot choose a wet biomass. So we need to dry the biomass for your characterization, like XRD, XPS, TEM, FE. Okay, so to know how the metals are going to be embedded into your carbon matrix, so to know those details, we need to dry the things, the impregnated biomass. So then that has been finally powdered, and it has been used for your analysis part. Okay. So whereas for our gasification, we have directly used this wet biomass, and then we have chosen it. So let me share the results that we have achieved, or that we have performed with the banana pseudostem. Okay. So this is your first part that we are going to talk about. So that is nothing but your metal loading. So how can you load a metal onto a biomass, right? So for that, what we have chosen is, we have taken the biomass, we have changed the pH of the biomass slurry solution, so that we can load the maximum metal onto the surface, right? So if you look out at the zone of positive charge, that is at pH less than ZPC, where you see it is going to be have a positive charge. Here your metal ions and the hydronium ions is going to get compete with each other, and as a result you see that the metal loading is going to be less over here, right? You see this is pH, and this is the mole of nickel per kg of biomass that it is going to happen. Now as soon as, even at the higher pH, you see there is a uh, uh, the the biomass loading is little bit high at 8, but after that it has been decreased to 10. The reason why it might be there is, so as soon as during your impregnation, so it forms, or the precipitates of your metals, it is going to get onto the surface, and as soon as you wipe it off, so it's going to be reduced. So as a result, you see that even though you have a high concentration, but we have chosen a pH of 0 point charge, that is where your the initial and final pH line is going to intersect with your 45-degree line. So that gives you the pH of 0 point charge, where you see that we make sure that the charge is neutralized and the loading of your metal is going to be very high. So you see that for a banana pseudostem, we have loaded with 3 materials, that is nickel, iron and ruthenium. At the pH ZPC, that is 0 point charge, pH was found to be around 6.4, 5.3, 5.8, and a metal loading of nearly 0.98 mole of nickel, and 0.83 mole of iron, and 0.79 mole of ruthenium has been loaded onto your biomass. Okay. Now what happens during this biomass is, whatever the salts that are present, or the cations that are present, like sodium, calcium, magnesium and potassium, so these become hurdles for us when you are going to treat them at supercritical conditions. As I have already mentioned, that water becomes non-polar solvent in the supercritical conditions. So as a result, these salts, that is like the cations that I am talking about, like sodium, potassium and calcium, so these gets precipitated at supercritical conditions, and thereby corrodes the material of your reactor. So what we are doing in this process is, we are replacing these alkalis and alkaline earth metals with your metals that we are talking in the form of nanometals, like the nickel, iron and ruthenium. So these metals replaces the alkalis that are present in your biomass, and you see this is how typically your treated biomass looks like, right? So you have a biomass which is going to be initially, and then when we are impregnating it with the nickel, this is going to be converted something like this, where you are eliminating your alkalis and alkaline earth metals during impregnation process, and you are replacing the alkaline and alkaline earth metals with your metals that you are loaded onto the things. Okay. So before we go more in detail about the thermal degradation, one has to perform this proximate and ultimate analysis to identify the volatile matter content and fixed carbon content. So you see that the volatile matter content is around 75% or 76.5 for banana pseudostem. Fixed carbon is around 4.86, and its ash content is 8.64 for raw biomass. Now, as soon as you are impregnating with metals, so as you see that the metals falls under the category of ash content, so you see your ash content is going to be significantly enhanced, which conveys us that there is some loading of metals that is going to happen or happened or that occurred during the impregnation process. And you see that the carbon, hydrogen and nitrogen content is also going to be significantly reduced to a significantly reduced. And you see that since nitrogen content is slightly increased for nickel, because we have used nickel nitrate as a salt, and whereas the other things is going to be decreased, like your N is going to be decreased with case of your ruthenium and iron. Not only that, so we have already quantified the biomass in terms of three components, that is essential contents of your biomass, that is cellulose, hemicellulose and lignin, and also the extractives. So the banana pseudostem have a cellulose content of 38.36, cellulose content of nearly approximately 29, and lignin content of 17, and they have extractives of around 15%. So these three parts is going to be contributed to a greater extent, where you are going to convert them into your gaseous fuels. Okay, so before we go more in detail about the degradation, one has to understand how these metals are incorporated into your biomass matrix. And you see there is a variety of FTIR. You see that there is a OH stretch which is going to present because of alcohols. This stretch is going to happen because of your attachment of your metals or interaction of your metals with your alcoholic group component, that is cellulosic components that you are going to have happen. You have a 1630, which is a CC stretch, which is related to the alkenes, and you have the one which is related to the alcohols, so that is 1156, and you have 1033, which corresponds to your alcohol one. So you see this is going to be very much less, which indicates you that there is a interaction between the metals and the functional groups that are present on your biomass matrix. Okay, so before we go more in detail about the degradation studies, one will be interested to know how the degradation profile looks like. If you see the degradation profile, you see that the banana pseudostem raw, it is going to have nearly almost 35% as its residue, right? So this dashed line that you are talking about, so is your raw banana pseudostem. Okay, so and you see it is going to be, the degradation process is going to be converted, classified into three stages. The preliminary phase is your removal of your moisture content, second one is your cellulose and hemicellulose stage, and third one is your lignin degradation. And we have a sharp intense peaks which corresponds to your degradation or the path breaking of your particular molecules that you are going to have the things, right? So if you see that the nickel is going to give result in lowest conversion, that is less than 25%, and one has to keep in mind this is after loading of the nickel. So if I'm going to remove the nickel content also from the biomass, the conversion is going to be less than 10%. Okay, so once we have done that part, so you see that there are sharp intense peak, that is GTG peak somewhere around 300, which makes or which conveys that there exists the degradation of your molecules, like cellulose and hemicellulose is going to degrade in this particular portion. And we see that for specifically iron, you have a peak above 400 degrees centigrade, which says that the ring components like lignin and everything is going to be effectively cleaved in the presence of your iron compared to that of other two materials. And furthermore, there is one more. If you see that the presence of your metals have resulted in higher peaks compared to that of your raw peaks. So now what does that mean? So that means it is not only the cellulose that it is going to happen, it is promoting the degradation of your compounds. And not only that, there is one more reaction that is going to happen, that is the reduction of metal oxides to active nanometals during this degradation process in a single step. So where you see that this carbon nanometal composites is going to be converted into carbon nanometal hybrid materials during this hydrothermal treatment. Okay, so this is typical XRD profile of your different raw impregnated biomass, raw and impregnated biomass with different metals like nickel, ruthenium and iron. You see the sharp peaks that are there between 10 to 25 degree of your 2 theta values. it is corresponds to your crystalline forms of your cellulose, which exist in cellulose 1 and cellulose 2 forms. Okay, and you have a nickel oxides that is present for your over here, which is peaks that is going to be represented over here. You have Fe2 plus and Fe3 plus that is going to be there for case of your iron impregnated biomass. You have a sharp peak of active ruthenium over here, very small sharp peak. That is, you have the ruthenium is going to be reduced in the presence of your banana pseudostem to a smaller extent. As a result, you see that ruthenium is going to exist in its active metal form. That means from your oxide form, it is going to be reduced to the metallic form. Okay, so these conveys that the metals are embedded into your biomass matrix, and this biomass matrix is now enriched with your metals by replacing the alkalis and alkaline earth metals. Okay, so before that, I think I should show you the TEM. Okay, then I will come back to that XRD profile one more time. So if you look out at the TEM profile over here, so we see that the particle size is going to be less than 100 nanometer, which conveys that the biomass or the metals that are embedded in your biomass matrix is a nanometal composite of your carbon, where your metals is in the size range less than 100 nanometers, and that gets encapsulated in your biomass matrix. This is your nickel one, this is your ruthenium, and this is your iron one. So all this, the particle size was found to be typically in the range of, for nickel it was around 40 nanometer, whereas ruthenium it was around 50 to 55 nanometer most probably, and for iron it was around 30 to 45 nanometer. Okay, so these conveys from the TEM analysis of this metal impregnated biomass, we can convey that the metals that are present or that are embedded in the biomass matrix are in the nano range. Okay, so now let me just come back to our original discussion, that where we are doing our XRD and XPS analysis. Now, if you look out at the XRD profile after the thermal degradation of your or hydrothermal treatment that we are going to see, you see that there are peaks which are related to cellulose. So those gets disappear over here. So the peak that is B is going to be the char that has been obtained after the treatment at 300 degrees centigrade, and the char that has been that has been obtained at 600 degrees centigrade. Just give me a second. Okay, thank you. Okay, so if you see the peaks that are related to the cellulose, those get disappeared over here in your 300 degrees centigrade char. That means whatever the cellulose that was present in your actual biomass, that gets degraded when you are subjecting your biomass to 300 degrees centigrade. Now you have a very sharp, intense peaks that are related to your nickel oxide, that is the diamond shaped ones over here. You see this one peak at 45 degree and peak at 37 degree, and you have a peak at around 61 degree of your nickel oxide, and you have a peak at 76 degree for your active nanometal of your nickel, that is Ni, right? So you have a short, this peak corresponds, these two peaks corresponds to your face center cubic centimeter, that is you have a Miller plane of 111. So where it is a the formed crystalline material is going to be in the face centered cubic structure, and which enables the nickel is mostly in the form of face centered cubic structure. Apart from that, it has also have the some kind of crystals are formed with Miller indices of 100 and 222. Okay. Now, to further confirm the oxidation state of these metals that are formed during the impregnation and during the treatment. Okay, that is thermal degradation. We have performed this X-ray photoelectrospectroscopy, where we found that the nickel is mostly exhibited in the form of +2. So this is the composite red curve that we are going to see. This has been deconvoluted, and we see that the pink peak, which is going to have over here, corresponds to, at the binding energies of 855 and 870, 880, which corresponds to our Ni2, that is nickel oxide particles, and with the corresponding satellite peaks of light blue, which are represented in light blue color and the dark blue color. Okay, so these binding energies conveys that the nickel existed in the form of Ni2 plus, that is in the raw biomass that you are talking about. This is banana pseudostem impregnated with your nickel. Then if you look out at the chart that it is going to be formed, you see that instead of having the spread of your curve, the composite curve, you have a sharp intense peaks of your composite curve, and which when it has been deconvoluted, you still see that nickel is still existed in the form of Ni2 plus itself for the corresponding binding energies of whatever it has been reported with the impregnated biomass. Now, but as soon as you see when you are taking it to the 600 degrees centigrade, so you see you have a sharp intense peak of around 857, okay, which conveys that the binding energy at the electron, so which corresponds to the binding energy of your active nickel nanometal. Okay, so active nickel metal, it is not. So we have already confirmed that it is from the TM analysis that nickel existed in the form of nanomaterial. Now, as soon as you see that the binding energies that corresponds to our 857 and 874, so that corresponds to your active nickel metal with the corresponding satellite peaks of satellite peaks at 2p 1 by 2 and 2p 3 by 2. So which conveys that when we are increasing the temperature from 300 to 600 degrees centigrade during the hydrothermal degradation, we found that these metals are going to be reduced, or from the oxides of that is in +2 oxidation state, which are at from the metal impregnated biomass, which is at normal room temperature and at 300 degrees centigrade. So these gets converted into active nanometallic forms. Okay. Now the same thing has been even observed with our ruthenium also. Ruthenium, when we have impregnated them, we have a sharp peak of active ruthenium which has been formed around 39 degree of 2 theta. But whereas if you are going to treat it at 300 degrees centigrade, we see that it forms both oxide ones, okay, but majorly it forms the active forms of your ruthenium, that is which is around 44 degree of 2 theta. At 2 theta of 44 degree, you have an active ruthenium metal. So RuO means 0 means, that means in its metallic form. It doesn't have in any of your oxidation state, that is not in +1 or in +2. Okay. And whereas you see that most of that 300 degrees centigrade, that ruthenium existed as in the form of ruthenium oxide. Okay. Then if you look out at the XPS things, like, we made sure that we have deconvoluted the composite red curve that it has formed. You see that the blue one at the binding energy of 277 point something, 277.6, binding energy of 270 for a binding energy of 277.7 electron volt. We see that the ruthenium existed in the form of actual metal, active ruthenium with the corresponding satellite peaks at 3d 3 by 2, and at Ru ruthenium also existed in the +2 and +4 forms during your impregnated state. Now even at the 300 degrees centigrade, we see that ruthenium existed in all the three forms, that is in ruthenium oxide form and also in the +2 and +4 forms. But whereas if you see at 600 degrees centigrade, whatever the intensity of the blue peak is going to be enhanced, which it makes sure or which conveys that the reduction of your metals is going to happen at the supercritical conditions that we are using it, that might be using from the carbon source or from the reaction medium itself. Here we have any interesting phenomena. So where we see that, as I've already mentioned, that the XRD phenomena, that the XRD profile or the XRD spectra for the char that has been obtained at 300 degrees centigrade and at 600 degrees centigrade. So you see that iron existed mostly in its oxide form. You have a sharp peaks, that is, I mean, very sharp, intense peaks, which is around 74 degree for your to the top 74 degree over here you see. And you have one more peak, sharp intense peak, which is coming around 46 degree. So where you say that alpha actual metal of iron is going to be there with 100 Miller indices plane, and you have oxide, that is iron mostly existed in +3 form. That means here we can conclude that thing, it forms a core shell type of nanoparticles of your iron after the hydrothermal treatments, where you have a core of your iron nanoparticle which is surrounded by your oxide layer of your iron. Okay, so the reason why it might form in a core shell nanoparticles of iron and iron oxide is because iron is very active or very vulnerable to the oxygen environment. Now, as soon as you see the oxygen environment, it gets oxidized quickly, right? And the second thing is, during your treatment process, initially it gets the oxide forms of the metals is going to be reduced. Once it gets reduced with the kind of carbon source, or when it reduces to the medium, now once with the formation of your intermediates, these intermediates which might be rich in your oxygen comes in contact with iron, and thereby it forms the oxide forms of iron. As a result, you see at the 300 degrees centigrade, we have peaks that are related to the active metallic forms of iron, and whereas at 600 degrees centigrade, you see that you have more peaks related to the oxide form. So this means it conveys that it forms the core shell nanoparticles. And whereas from the XPS analysis also, it has been confirmed that iron mostly existed in the +3 state, even at 300 and 600 degrees centigrade. Okay, so to further confirm the presence of these metals on the biomass matrix, we have done the SEM EDX analysis, that is scanning electron microscopy and electron dispersive X-ray analysis to quantify and to understand the morphology structure. You see that you have a plain structure, or your structure is going to be very smooth for a raw banana pseudostem. Now, as soon as we are performing the impregnation experiments, we see that these surface is going to become rough and get distorted with the loading of metals onto the surface. The nickel content of as high as 22.54 has been obtained in terms of weight percent. And you see that out of all the three metals, the nickel loading has been high, followed by iron and ruthenium that we are talking about. Okay, so all these convey that the carbon nanometal composites has going to be formed during the impregnation process, and these impregnation biomass, when we are subjecting to the hydrothermal gasification, so these going to be get converted into your hydrogen rich fuel gas mixture. Now, to understand the performance of this hydrothermal gasification of this metal impregnated biomass, so we have designed and fabricated this experimental setup. So this experimental setup comprises of an inert gas cylinder. You have a thermal furnace and a tubular Inconel reactor, and you have a gas liquid separator, a moisture trap, and a gas chromatography for the analysis of the gas mixture. And not only that, we have a thermocouples and pressure gauges and high pressure valves for the safety and also for the conduction of your experiment. So now let me explain you the experimental procedure, how we have performed the experiments. So during before you start the experiment, we make sure that all the lines that are associated to the reactor, we are purging with nitrogen to make sure that it is free of any of your oxidizing environment. and then we are loading the reactor with the known quantity of biomass, typically in the ratio of 1:10, and then we are sealing this reactor, placed it in a furnace where the reactor is going to be heated in a furnace to the desired operating temperature of nearly 600 degrees centigrade. Okay, so once it is going to be reached to the desired operating conditions, before we place the reactor inside the furnace, we make sure that the valve, that is the valve inlet and the valve outlet over here, it is going to be closed. As a result, you see it forms a closed system, and then if you are heating it, then your pressure is going to be automatically built inside the reactor. Now as soon as you are heating the conditions, so the supercritical state is going to be achieved after some time. So once the supercritical state has been achieved, that means from the pressure pressure gauge, we would be able to understand what kind of pressures we have achieved. Now if the operating conditions are beyond the critical point of water, that is 22.1 megapascal and 373, since we are operating at 600 degrees centigrade, so then we are allowing the reactor to stay at those mentioned operating conditions for a specific period of time, that is called as residence time. And once the residence time is being completed, then we are opening the outlet valve. As soon as the outlet valve is open, the product gases, the product mixture is going to be passed through a 2-micron filter to make sure that there is no particulate matter that enters into your gas phase analysis system. So it passes through the 2-micron filter where it enters to a gas liquid separator. So in the gas liquid separator, gases and liquids get separated, where we are able to get the liquid residue at the bottom for further analysis. The gases that is going to be formed, or it is going to be opened through the top valve, where it passes through the moisture content just to make sure it is free of moisture. We are using the silica gel over here to capture all kind of moisture that is present in your gas mixture, and this is directly fed to your gas chromatography, which works on a principle of TCD to estimate the quantification of our gases that is going to be generated. Okay, so now I hope you are clear with the performance or how the experiments is going to be conducted. So once the experiment has been conducted, so we have defined some of the performance parameters where we can quantify the performance of your process that we are dealing with. Now, as you see, we have defined two terms, that is carbon gasification efficiency and the total gas yield over here. So now carbon gasification efficiency has been defined as the amount of carbon that is present in your feed, present in your product to that of the carbon that is present in your feed. So that gives you the carbon gasification efficiency. Total gas yield is defined as the quantity of the gas that is going to be generated per gram of biomass that has been fed to the system. Hydrogen yield is being defined as the quantity of the hydrogen gas that has been generated per gram of biomass that has been fed to the system. So now if you look out at the operating conditions, so we will start with raw. So we see that at 300 degrees centigrade, we have a hydrogen yield of 0.74, and we were able to get a maximum of only 4.2 millimole of hydrogen per gram of biomass that has been fed to the system. Okay, and if you look out at the total gas yield also, the gas yield is around 6.74 at 300 degrees centigrade, whereas it is going to be raised to 13.64 for raw biomass, and the gasification efficiency is around 30, whereas it is 46.6 at your 600 maximum operating condition. So as we already know that this degradation of biomass is an endothermic in nature, and we see there is these gas yields and carbon gasification efficiency both has been improved significantly in the presence of your when you are using this hydrothermal treatment. Now, as soon as we are introducing the metals, nanometals into your biomass matrix, now you see there is a huge jump in your hydrogen yields from your 0.7 mole to almost all 11.1. That means almost all 12 times or 11 times higher than the actual gas yield that is going to be, sorry, 3 times higher than your raw biomass yields. That is at 600 degrees centigrade. You see, we are getting only 4.2 millimole per gram of hydrogen, but whereas at for the same thing, for the same biomass, if you are having a nickel in that, we are going to have almost all 11.1 millimole. That means almost all 3 times compared to that of your raw biomass. Whereas iron, it is almost at 8.04, that is twice that of your raw biomass. Ruthenium, it is almost at 8.83. Not only the hydrogen gas yields, but you have also see that the total gas yield is also has been significantly improved, right? So you have the nickel is been almost all the total gas yield in the presence of your nickel, it is going to be almost all doubled, and the carbon gasification efficiency, which was around 46, has been improved to 73 in case of nickel, whereas for iron it is 62.65, and for ruthenium it was around 64%. So now all these experimental results convey to us that the presence of these nanometal in the biomass during the impregnation stage helped us or enhanced the quantity of not only the total gas yield, but also improved the carbon gasification's efficiency. Along with that, they have selectively promoted the hydrogen gas yield to a greater extent, almost all twice or 2 to 3 times to that of your raw biomass that we are talking about. Okay, so now the same thing has been mentioned. So if you look out at the gas yields, individual gas yields that has been formed at 300 degrees centigrade and 600 degrees centigrade, you see that the hydrogen gas yield, which is very less at 300 degrees centigrade, have significantly increased when you are increasing the temperature from 300 to 600 degrees centigrade. Now, the reason why the hydrogen gas yield is going to be significantly increased is because of 2 reasons. So one is your water gas shift reaction, other is your cracking and reforming reaction. Now, whenever you are going to have a cracking and reforming reactions, you see that the hydrogen gas yield is going to be significantly increased. Not only that, you see that with the increase in your temperature, your carbon dioxide yields is also going to be increased significantly, which conveys to us that the reforming reactions of the intermediates, not only intermediates but also the gas forms like methane and CO undergoes the water gas shift reactions to selectively enhance the hydrogen gas yields. Now, as soon as you are increasing your nickel content or your presence of nickel, you see that the quantity of your carbon monoxide, that means you see that there is almost all negligible in case of banana nickel impregnated banana pseudostem at 600 degrees centigrade, which conveys us that the nickel has selectively promoted the reforming reactions, thereby enhancing the hydrogen gas yields to a significantly, that is nearly 11.1 millimole per gram. And not only that, it also increased your carbon dioxide yields, which conveys that it is going to be selectively promoting the reforming reactions, and thereby enhances the overall gas yields that we are looking for. Now, coming to the ruthenium and iron, the ruthenium also followed the similar pattern, but however, you see the gas yields are less compared to that of your nickel one. And ruthenium have a high activity towards the cleavage of CO bonds and results in the formation of methane also. Now you see that if you look out at the carbon dioxide yields and methane yields at 600 degrees centigrade, you see they are almost all equal, which means that the carbon dioxide that is formed is going to be cleaved in the presence of your ruthenium, and thereby you are able to enhance the methane yields also. That is another fuel gas, that is natural gas that we talk about. Hydrogen mixed with methane is going to be significantly improved in the presence of your ruthenium. Now, interestingly, if you look out at the iron, so I was not able to present you the liquid content, then it would be easy for you to understand. As I have already mentioned, we see that the iron have a high activity towards your ring components, right? That is your benzene or other any ring phenolic components. All those components that you see which are having a ring structure are effectively cleaved in the presence of iron, As a result, we see that hydrogen yields are also going to be significantly enhanced in comparison with our raw yields. So, and overall, we can conclude that the presence of carbon nanometal composites in your degradation process enhances the hydrogen gas yields to a significantly, and not only that, it also promotes the total gas yields and carbon gasification efficiency. Now, one more key point that I would like to mention over here is, see, the main problem that we were talking about is that catalyst deactivation, right? So if you look out at this in situ process, so here we don't have any problem of carbon deposition or deactivation of the catalyst. The reason why I'm saying that we don't have the problem is, see, you see that we are impregnating the metals right at the front end itself. Now we are treating the metal embedded biomass matrix during the hydrothermal treatments. These metal embedded biomass matrix, they undergo the reduction process to form the nanometals during the degradation itself. Now, as a result, you see when it forms the nanoparticles, it is going to have a high surface area. Thereby, it enables the interaction of your intermediates with the metals and thereby promote the degradation of the thing. So one more point that I would like to add over here is, if you look out at the TOCs of these liquid streams that has been formed over here, so the raw biomass have a TOC of nearly 5,500 ppm. Now, as for the nickel, it was around 600 or 550 ppm. Okay, and whereas for ruthenium it was around 1200 ppm, and whereas for iron it was around 1500 ppm. So now this is the raw the TOC of our raw biomass was around 5,500. It was being reduced to almost all 600 ppm, which makes sure that these metals that are formed is promoting or enhancing the gas yields by interacting with the intermediates that are formed during the degradation process. Okay, so with this I'm going to stop over here, so we can discuss about this carbon nanometal things in the maybe during our next session, where I will be discussing more in detail about these nanometal composites, how we can use it even for environmental and biological applications, maybe in the tomorrow's session, that is from 11 to 1 p.m. Okay.
Thank you, sir. Dear participants, if you are having any questions, you can ask sir, or you can post the questions in your chat box available on the website.
Yeah, so the floor is open for questions, so you can ask any questions.
I request once again all the participants to post the questions to sir, if you are having.
Thank you, Sunil.
Okay, I think that the students can well able to understand the lecture, and again the next session will be starting by 11:15 by Dr. Ravi Shankar on polymer rheological abrasive semi-solid adhesive cutting tool materials, and Shiva Mohan Reddy sir next class will be at 11:15 to 1:15 tomorrow. That is the last day of our course, and he is going to give a lecture on nanobiocomposites for biological applications.
Okay. Yeah, I'll be including the environmental applications also,
So,
not only biology, so we can include both the environment and biological applications.
okay, sir. So, the lecture was very impressive and informative, that it can pay a way to do further research work, and sir has given a glance on us. So even if you are having any questions, you can contact through an email to sir. Sir, once again, thank you for your nice contribution for this course.
Okay, I
Thank
once
you, sir.
again thank you all the participants for being very nice and cooperative. Thank you very much. We'll meet
Thank you.
once again in the tomorrow session. Thank you.
Yes, sir. Thank you.